Welcome everyone, and thank you for joining us today. And if anyone has any questions or queries, either for the speaker after the session, or if you're having any trouble accessing links, please feel free to email us at webinars@sstafrica.org.za. I'm going to hand over now to Yusuf. Whenever you're ready, Yusuf, you can take it away.
All right. Thank you very much, Tara. Yeah, you're all welcome, and sorry. All right, good. I believe I'm loud and clear, and thank you very much actually for attending. Before I go further, actually, I would like to use this opportunity to thank SST and NREF for allowing me this opportunity actually to look at plastic waste management from a thermochemical point of view. Yeah, we're still celebrating our 100 years at Wits, so that's why I have that actually. But yeah, that's it. This morning, well, depending on time of the day, I will be talking about a very topical issue that seems to pose a lot of threat as far as sustainability is concerned. And here we are making reference in particular to plastics. There are quite a number of policies, efforts to ensure that actually plastics are properly utilized or managed. I am coming, or rather my talk today will be coming from a point of view of the structure of plastics, how they could easily be decomposed and transformed to other materials. As such, I will give an overview of plastics from their chemistry, structures, say one or two things about environmental threats, talk about the existing plastic management techniques and where there are pitfalls, where there need to be improvements. Then before we move to energy, fuels, and petrochemicals, I will say one or two things there because our target when we do a thermochemical conversion is to actually get one of the mentioned items. I will highlight a few thermochemical conversion processes. We have 30 minutes, so I won't make it as detailed as possible. And I will also say one or two things about the products we are likely to get when we carry out these thermochemical conversions, and I will conclude based on our discussion, and I will be more than happy to discuss any questions or interactions we may have to do. All right. It's interesting for us to know that actually plastics, despite the challenges they pose to the environment, to humanity, we still continue to make use of them. And I think a typical question that one will want to know is, why are we still going ahead with plastics? And going through, you will realize actually there are quite a number of reasons why making use of plastics is worth it. One of them being that actually they allow room for a wide variety of options. I mean, you must, whenever you talk about plastics, they come in different forms. Some of them lightly dense, some of them heavily dense. Now that aspect alone, that they are able to fit into the various aspects of our busy lives, gives them an edge over a lot of other materials. Now, apart from them being versatile, you could use them in other places. They also have various properties that are applicable to the time of need. Some of them are chemical resistant. To a certain extent, some of them have a very high temperature of ignition, which makes them suitable actually for certain applications that require high temperatures. Now, apart from their various properties, another thing actually that makes them easily utilized or actually attracts humanity to them is the fact that the industry that produces plastics, as far as chemical processing is concerned, is the most advanced and well-known industry. That still remains, should I say, the most reliable in terms of production of chemicals, raw materials, feedstocks, and for that reason they're used. The other thing that makes plastics actually still welcome despite their challenges is actually their convenience. They're very, very convenient. They are light. I mean, in the olden days, You will want to do a network of water pipe in your house. You use cast irons. After 3-4 years, there's a lot of rust. You don't want to do that now. You want to work with light materials, and you use PVC actually, which is rust proof. Actually, those plastic bags you take, you reuse them and things like that. And I think a very important criteria is the financial component they come with. They are very, very cost effective compared to other sources of other types of packaging, among others. Having said that, at least, we still know that there are challenges with these plastics. So we've looked at them actually from a point of view of being convenient. But do we have a good understanding of how these plastics are formed? What makes them unique and what gives them these particular properties? I will start by going through the basics actually of what a polymer is. I will assume here there are two objects, A and A, that have been bonded together. I mean, it's as simple as you have two paper clips and you brought them together. To a certain extent, they may come up with new properties that are different from the first A and A separately. And if that is a monomer, that is the smallest building block. If you were to have 5 of them, you'll probably have an oligomer. But if you have so many of them that you're not limited, you will have what you refer to as a polymer. Now, we have another A and A, and we have another A and A. And for some reason, the chemistry actually allows them to form new bonds. Now, this gives me a longer material, which, from the point of view of chemistry, does not mean I have lost the initial identity of my component A. What it typically means is I have formed a compound that contains A. So the rationale behind it is, if along A, because I had AA, and if I had so many of it, I can simply call it poly A. And that is how you call all these your polymers: polyethylene, polyvinyl chloride. Actually, you talk about the building blocks and you add poly to it. So I'm happy. So, but if I can destroy this and come back to my AA, that means there are some potentials. But the interesting thing is the new A's that have been formed have properties that are different to the initial A's. Now go back to the end of the 19th century and the early 20th century. Actually, these materials, when they were discovered, they were very fascinating because they did a lot. I mean, there were not so much issues about sustainability then, and a lot of those working in the petroleum industry wanted to maximize their profits. And what it means is you have a lot of chemicals build these materials. Now let's look at something else. We have ABA, and if we want to make a polymer that will be poly ABA, what it typically means is we should have links and get our poly ABA. And that's also a material that has different properties. And it is for that reason that these plastics, which are a type of polymers, not all polymers are plastics, but plastics are polymers because they constitute polymers as their main building blocks. For this reason, they come up with a lot of properties. And interestingly enough, I can have a polymer or an oligomer that actually decides to cross-link with another one. It forms another material, the same thing or that. So these are all possibilities. So I want us to have that at the back of our mind, that this is where actually those properties come. Interestingly enough, with chemistry, once you change from one form to another, typically you will get a material. It may affect its ductility, it may affect its tensile strength, it may even affect its melting and boiling points. And this is where those unique properties come. Now, which are the major types of plastic? Now, you have your polyethylene terephthalate, high density polyethylene, your PVC, that is your polyvinyl chloride, your low density polyethylene, your polypropylene, and your polystyrene. Now, actually, from our discussion, you will realize that most of these things are just polys of certain materials. So this, I will want to mention it here actually, that I have my terephthalate, and here you have your ethylene. So this is one monomer. And if I begin to build a lot of it, all I need to do is just make sure I have these compounds, get a lot of them, and I mold them. They simply form a plastic like this. That is all the chemistry. And they come with a number of properties, actually. They are ductile, they are strength, They are strong and they are stiff to a certain extent. And that is why you're able to put a 5 liter of water in it comfortably. However, if you want to take 100 liter of water, you may look for something stronger. And typically, someone will want to work with a high density polyethylene. Now look at this structure. It's interesting to note that this is ethylene, just like we had ABAB, we just have ethylene coming up and building. Now, what makes it different from low density polyethylene? Because it's all ethylene, but this particular one is durable. And when I talk about non-biodegradability, to a certain extent, it's a factor of time. Because everything is biodegradable. It just depends on actually what time you're looking at. Are you looking at billions of years or just a few years? It's chemically stable and it has impact resistance. Actually, that's why it's used for heavier materials. Then the other one that is very common that has actually brought a lot of change to the building industry is your polyvinyl chloride. Now, this, we are moving away from our carbons already, and we're introducing chlorine. And chlorine is not the best of things, actually, you want to interact with. It means if for any reason there is some decomposition and this chlorine leaves, it's likely to find its way to some places, some water, things like that, and there could be 1 or 2 problems. But the good thing about these PVCs is they are rigid polymers. They are very light. I mean, take a 6-meter pipe and compare it to a cast iron pipe that we had, 50, 60, 70 years ago. The difference is clear. Despite the fact that these materials are from hydrocarbons, it's interesting to note that this one has a very high ignition temperature. And when you look at your electrical installations, there are a lot of them. Not for anything, but because they don't ignite at very low temperatures. And they also have dielectric strength. Yeah, those are among some of the properties that are of interest. Then you look at your low density polyethylene. Here we go. And with your low density polyethylene, basically the same like your other ethylene, but now this is branched. And this is to show us that actually just the configuration or how we arrange the atoms can affect the property of these materials. Something else I want to talk about is your polypropylene. Now with your polypropylene, it's a very good material actually, chemical resistance, semi-rigid, good heat resistance. When I want to synthesize my catalysts, I work at about 180 degrees, 200 degrees Celsius. This is the material I use actually because it's made for such purposes. Again, you could see the propylene, we're just repeating them. Then another important one actually comes from the styrene molecule. And if you were to take your styrene a lot and you build up, you get what will be called a polystyrene. Those are your cups. When you have your barbecues, actually your plastics, your plastic cups, among others, come with the properties of being rigid, brittle, and they have a moderate strength. Now, some of the things we need to note is that these materials all exhibit different properties. And when I say they exhibit different properties, it means it's coming from the chemical composition. All right, then we go further to see what we have. We've seen that actually the plastic have come with a lot of advantages, but at the same time, they pose a lot of challenges. And if you look at what they've been doing to the ecosystem, definitely you will realize that no, these are not the best of things. I mean, research shown that actually you produce more than about 10 billion tons of global plastics globally. But in this particular work, we'll look at some research actually that focused on about 8.3 billion tons of plastics. And let's see, how do they become a threat? Now, out of this 8.3 billion tons of plastics that are produced, getting to about 60% of them end up as waste. So the remaining people that recycle them, but 60% is a lot. Actually, we are talking of a scenario. It's practically burning these materials. And from what you can see, during combustion, typically those components that were initially there begin to get liberated, and you begin to get a lot of things. And at the end of the day, if you have some of your chlorine going into actually the soil, coming in contact with rain, you may begin to acidify your soil, which affects your plants. If you're not far from the coastal areas, actually, it will also affect the marine life. Human beings, when they inhale this is a problem as well. And more recent, actually, there has been a serious concern about global warming because you are producing gases that have some equivalence to CO2 and some of them being carbon dioxide. And as some ozone depletion is concerned, you also produce volatile organic compounds, and some of them contaminate the soils, which affects, like we mentioned. So that's what happens to the 14%. Nothing good. Another 14% aims at recycling. But once you go into the chemical industry, you know for sure that actually when you recycle, there is definitely a lot of losses. And you are assuming that the losses are about 4%. Fine and good. Those losses will definitely find their way. And what makes it worse is they have undergone a recycling process. And if there were macroplastics, there are no more macroplastics now. They found a state of either being nanoplastics or microplastics. This even poses worse threats than what we had earlier. In some cases, we may be able to close the loop actually and return some of the recycled materials that get back into the system. Some of them are new products, we keep recycling them. Now, the most traditional way of managing plastics, which we've been battling with, is landfilling. You dig a very big pit and you throw all the plastics. That is a potential threat because you have your tires there actually, which have quite a good amount of benzene, your carbon. And if there is a fire, it's a serious problem. But again, there is leaching. And that is why I say there's nothing that's permanently non-biodegradable. Actually, you could have some microbial activities and there could be leaching. And there's groundwater that gets contaminated. The soil also could get contaminated. And it also begins to affect the soil structure. And if you are lucky, some of it actually will go to meet fossil fuels and be recycled back into the system. At least that is a bit controllable when you talk about marine life actually ingesting, among others. So these are the threats and these are the problems. But let's look at the Sustainable Development Goals. Where do we find plastics? Plastics are practically everywhere. A lot of us forget that actually when you talk of zero hunger, most of the places actually you serve meals temporarily, you use polystyrene. That means plastics play a role there actually. You go to number 6, clean water and sanitation, plastics play a role. You still go further actually, you want to talk about responsible consumption and production, circular economy, plastics play a role. Climate action in terms of global warming, just like we saw, it plays a role. Life below water, it plays a role. So practically, plastics have roles to play throughout. And having said that, I will look at what is it we are currently managing and how do we plan to go further. Landfilling has a lot of challenges. It's been practiced in a lot of developing countries and some developed countries as well. You dig a hole, a very large pit, you keep them there, but they still pose a problem because when they leach, they get to migrate and actually there's contamination with underground water and soil. Recycling, one of the 3 R's, a term that is actually very interesting. It's a bit different from reuse. You want to change the material to a certain extent, but make sure it's used again. Then we have bioremediation. In the recent past, actually, a lot of microbial activities has been tried, and that is why even in your landfills, you have a lot of methane being produced. You have microbial activities, and these microorganisms are able to degrade these plastics and produce some form of potential gases. Then an interesting one that is actually being used is value addition. You take the plastics as they are, especially the high density ones, your polyprops, use them to build roads. I mean, in terms of tarring roads, they are used as bricks because some of them have such strengths, but you may want to actually just melt them first, mold them so that they take the new shapes and you begin to handle them in that manner. Then what we will discuss today actually, which ties into recycling, basically has to do with thermochemical conversion. We are taking the plastics as they are and we want to expose them to a particular temperature that is suitable to take them back to what they used to be. And as far as I'm concerned, I think That is a very important thing because we are able to take them back to their monomer state. So if we take them back to their monomer state, let's see, can we mold them to a chair? Can we mold them to something else? It's at our disposal. We've been able to convert them, and let's see what we can get out of it. Now, I would just like to touch a few things about energy, fuels, and petrochemicals. Energy, as we commonly know, is your ability to do work. But for that work to be done, there is something that actually requires some inherent amount of power to be released, and that is what you refer to as a fuel. And if you look at the fuel triangle, in most cases, that is combustible fuels. You will say, okay, fine, I want an ignition source, I want a fuel, and I want oxygen, and you'll get your combustion. But let's not forget, even the food we take is actually a fuel. So it gives us some energy, isn't it? So when we talk of the thermochemical process, when I talk about the fuel, I'm making reference to that one that leads to combustion. But one good thing about energy is it can be transformed from to another. So if I have a fuel, I can find a way of actually making it turn a turbine. And if I'm able to turn a turbine, I'm able to generate electricity. That's even great. And interestingly enough, these plastics contain carbon and hydrogen, which are the fundamentals of any fossil fuel or even your renewable fuels, actually, because when you look at your biomass, you are looking at the lignocellulose materials, actually. You are more interested in the carbon and hydrogen. The ratios tell you whether it will be a solid fuel, a gaseous fuel, a liquid fuel. The question is, do we have that opportunity actually to transform our plastics back to the states? If there is such a possibility, then there are a lot of opportunities. And this is why we have this diagram here in blue. At about 650 degrees Celsius, expose your PP, your PE, you will get some ethylene, you'll get some hydrogen, and you get some methane. And methane, basically, it's a mixture of one of the gases you use at home, or your C3, C4. And that is it. If I know how to do my Carnot cycle, I'm able to generate electricity. So that's good about the transformation. Now, when we talk about fossil fuels, they have a lot of challenges. They are part of the challenge is actually they lead to the formation of plastics. But I think the major one today is non-renewability. It's still a bit debatable. So we try to look at renewable fuels. It's not that renewable fuels actually do not give off CO2 when they combust. I mean, that's the basic principle behind combustion. You react with oxygen, you produce CO2 depending on the amount of oxygen. But the difference is you are not bringing the CO2 from a material that died 6 million years ago. You are probably bringing it from a biomass material that was used recently. So at least the net effect has been kind of counterbalanced. Then we also want to look at sustainable fuels. Sustainable fuels go beyond renewability because they do not only stop at being renewable, they make sure that at the end of the day, the future generation will not suffer from the use of those fuels. And if we look at our biomass, it's sustainable, it's renewable, but it still emits our greenhouse gases. So the question is, to what extent is it sustainable? There's been research on that as well. Now, so thermochemical conversion, again, basically uses temperature. And in the course of utilization of temperature, one good thing with chemistry is if the material decomposes, just like polymers were formed, you could also add to form new products. There could be alkylation, there could be aromatization, quite a number of approaches to building these things actually. So my feedstock, I will call them as hydrocarbons, general. It could be plastics, it could be biomass, to find how they differ and how we are able to control the process. And what do we get at the end of the day? We get fuels. Your fuels actually are applicable to your engines, internal combustion engines, cooking gas. You produce quite a number of petrochemicals, among which are your plastics. Then you want to generate electricity, actually. There are that thought of actually replacing coal with plastics so that actually you could boil water to get your steam, that you could drive a turbine. Alternatively, you could also produce your synthesis gas that actually could be used in generation of electricity. Now, I want us to have a look at 3 things here or three important processes. There are critical parameters here actually that aid to the conversion of plastics or any biomass. One of them is heat, which is the temperature at which we carry out the process is dependent on the heat. There is a catalyst. The important role catalysts play is they try to lower the heat, which technically translates to the activation energy. And if the activation energy is lowered, what it simply means is the amount of energy needed for that conversion becomes less, and technically you get a more efficient process. And these catalysts come in different forms, and the good thing about them is they can take A and convert it to C, or they can take A and convert it to M. So if I have the right catalyst and I want to convert my benzene to hydrogen, for instance, I just need to get the right conditions and I do that. Benzene may be toxic, hydrogen is more friendly but has its own problems. Then we have an oxidant, actually, which is in most cases required for you to have a combustion. Now, if you look at the outer cycle where we have combustion, the only material that is going in there is the oxidant. So for combustion processes, oxidant is critical. We should note that in most cases, this is done at elevated temperature. But what combustion really means is a reaction with oxygen to produce an oxide, and in most cases is a complete conversion. For instance, I can take oxygen and react with a carbon and I get CO, which is different from CO2. So combustion will usually lead to CO2. It's a complete reaction. Then we go to the next line, which is gasification, and it's unique. It's one of the most interesting ones actually, because it is one that produces gases for you, and you will require your heat, your catalyst, and your oxidant. For those of you that have had the opportunity actually to work with coal, the big coal players, when you talk about coal to liquid, basically that is what you go with. You produce carbon monoxide and hydrogen, which are very, very important platforms in the petrochemical industry. Give me carbon monoxide and hydrogen, I will synthesize whatever you want if I have the right catalyst and temperature. Then we go to the last but not the least, which is pyrolysis. And pyrolysis is also unique in the sense that it is one of the only ones that can give you a char. By char, I mean the solid material left, your liquid, which could be your tar, and your pyrolysis gases. So there we go. We've looked at processes that actually produce quite a number of things. But let's not forget, because they were not pure compounds initially, they will come up with a lot of things. And that is where the industrial plant is required. You may want a scrubber, you may want an absorption unit to actually remove some of the impurities. Combustion process, if you were to combust the plastic, it's as simple as taking the plastics, make sure there is air, you heat it, a source of ignition, and what do you get? Carbon dioxide and heat. You'll be surprised that actually this heat will be good enough to boil water for you. But I'm not saying you should go and do that actually, but it's good enough to boil water. But the problem with these processes is, again, we're having our greenhouse gases. And that is where the debate comes. At what scale are you producing? In terms of CO2 equivalent, actually, how bad is it? And this is defined by quite a number of processes. So that's combustion for you. You just take your plastics, excess oxygen, you produce heat and CO2. Heat can do a lot of things actually. It can boil water to produce steam, which can actually be used to turn your turbines for electricity generation. Then pyrolysis. Now with pyrolysis, we run away from the oxidized products. So what we do is we degrade the material in the absence of oxygen. Whatever you will do, make sure that there is no air going into that vessel, because air contains oxygen. There is no oxygen going into that vessel. So we elevate the temperature from 300 to 900 degrees Celsius, depending on what we want to do. We have what you call the slow pyrolysis, the fast pyrolysis, and the flash pyrolysis, actually. All these are very much dependent on how fast you raise the temperature. we may produce a lot of products that we're not happy with. That's where your catalyst comes in. Take a catalyst and try to be selective to what you want to produce. So what it simply, the good thing about pyrolysis is I can take a wide range of products. You know, when you handle plastics, you need to sort them. This can go back to this can go back to this can, no, but the temperature now allows it to degrade. I'm doing it in the absence of oxygen. So I'm going down, actually, I'm producing quite a lot of things. It's that carbon and hydrogen that is there, irrespective of the state. So it allows me for better things to produce. And good enough, it has liquid oils, your char, your gases, and it has a high heating value of 43 megajoules per kilogram. Just to give you an idea, your gasoline that you use in your cars will have about 46 megajoules per kilogram, which actually makes this product quite good. If you were to look at the schematic, if you are thinking of designing one, all you need is a system that actually will shred your plastics, and you send them down to what you will call your reactor. At the control temperature, there is no air here, no oxygen. You have your catalyst. When the products come out, because they are coming out about 800 degrees Celsius, they are very hot. They won't come out as liquids. You definitely want to pass them through a condenser, what you may call a heat exchanger. And these condenser will have an inlet and an outlet. So let's say they come in at about 500. I mean, you have a train of condensers. Probably they are living at 40 degrees, which will be a mixed oil. But remember, some gases were formed. Even at 40 degrees, if you have methane, it will still be a gas, so the gas will leave. And here you have a mixed oil. You take it, you do your analysis, and based on that, you will design a tower that will be able to fractionate this material. Gasoline, diesel oil, kerosene, jet fuel, and that is typically one way of recycling your plastics. Then we go to gasification. Gasification differs from combustion in the sense that we manage or control the amount of oxygen. We don't want to produce CO2. One of the materials has very good calorific value is a mixture of carbon monoxide, CO, and hydrogen. And the only way we can do that is we need to make sure that hydrogen has been injected, but it's not in such a quantity that will lead to the production of CO2. But you see, with reactions, there are certain things you cannot control. And as such, you produce things like methane and CO2. But the idea is to produce them in very little quantities so that you will have your synthesis gas as the major player. Now, this gas you produce, it can be used in internal combustion engines. It can be used in turbines to generate electricity. And this is the fundamental of production of a lot of things. I can produce my methanol, ethanol, quite a lot of products actually. And this process dates back to as early as 1800s. This is typically what it looks like, your gasifying unit. You will have a hopper. I mean, it's don't look at this reactor as something, just consider it to be a container that has a place where I will throw in my feed. It has a place where I will inject some air, and it has a place where the gases will leave. And typically a number of things happen. As you pass the plastic in this zone, it undergoes drying. So by drying, if it contains any moisture, all the water molecules leave. So it's being heated. Now, if you are heating a material and there is no water, remember you want to run away from oxidation. And that water molecule as well, you want to get rid of it. No, you don't want any oxygen. And now you want to decompose at this stage. And when you are decomposing, a lot of volatiles will come out. Carbon monoxide, hydrogen, water if you still have others, and H2O if you still have others. So there we go, actually, gasification. And yeah, those are the products. And here you have the gasification range, where basically your materials that were produced actually react with the solid materials, and finally you get your oxidation. So where are your products? You get your ash here. You will also collect your some of the liquids, and you have your, you're only getting your ash. Let's not forget this is not pyrolysis, it's gasification. So we are targeting the gases this place, and we take them to a scrubber. If it's carbon monoxide and hydrogen, we go ahead to use them for other processes. Hydrothermal liquefaction. Now, I decided to look into this because some of the plastics we get actually come from marine origin, or in other words, from the seas. And what that typically means is they contain a lot of moisture. Do we really want to get rid of that moisture? If we don't, this is where hydrothermal liquefaction comes in. It uses the pressure of the moisture to exert a certain pressure actually on the plastics when they are heated and they form liquids. And for that reason, we say it uses autogenous pressure, and you are able to produce liquid oils. So generally, thermochemical conversion of plastics, if I were to look at it on a chart, one way of actually managing them, because we have about 60-70% of them that are still being thrown away. And research is ongoing, plants are being produced. We can gasify. If we gasify, we can produce energy and synthesis gas. We can do pyrolysis, and after pyrolyzing, we reform the products, we can produce hydrogen. We can crack them, in other words, break them into smaller molecules. We produce our chemicals and fuels. We can expose them to pyrolysis, fuels, chemicals, and char. Hydrothermal liquefaction, we produce our bio oil and biochar. Interestingly enough, this biochar has proven to be a material that enhances soil fertility. In other words, with biochar, you produce a porous material that, if injected into the soil, it helps as far as fertility of the soil is concerned. And basically, these are the things I mentioned earlier. A char is a solid material. You could also get your activated carbon. These materials are porous. They are good sorbents. And in fact, there are cases when someone ingests actually a poison. We are not hoping for that. Actually, what you are given is porous materials because they are able to trap those molecules. You are told to swallow this, and basically it treats it. They are used for treatment of certain gases. Then we go to our gases. If we produce methane, excellent, an excellent fuel. Carbon monoxide and hydrogen, excellent fuels. They could be used actually in boiler systems, or they could be used as they are actually to generate electricity. We have liquid oils, and once you have liquid oils, all you need to do is to get the right internal combustion engine, fractionate them. A certain fraction will be your C5 to C9, which will be similar to your gasoline. You move to your C9 to about C14, to about C14, which will give you a kerosene, avia, jets, fuels, and that is it. And you could use them for blending, among other things. Then finally, there are also energy carriers. Actually, they produce a lot of energy. They contain energy. When we transform them from one form to another, they actually liberate heat, which will be of benefit to us. Now, in conclusion, I tried very much not to dwell very much into the technicalities, but that picture there is somewhere on your way to Cape Town. It's an ideal situation, what we should have, sustainable systems everywhere looking green and good. It may not be very visible, but the fact is plastics are a convenience, but they come with sustainability challenges. And that is something that needs to be tackled. Thermochemical conversion of plastics is very promising. Detailed work needs to be done, however, determine to what extent are they sustainable, and wide selection of products can be produced from thermochemical conversion of plastics like we did see. So I still believe one of the ways actually to manage waste plastics is taking them back to their original state. And if we don't want them, we produce something else from them. Thank you very much. That was the ideal situation, but this is a concerning situation. You could see what plastics could do actually to the ocean, and that is supposed to be a waterway actually that has been plugged by plastics. And for me, what you have here is a fuel, because if I can take that sludge and I take those tires, it has a lot of potentials. The same thing with those plastics. But while converting, they need to be converted in an ethically and acceptable manner. Once again, thank you very much for allowing me sharing my thoughts with you. And yeah, I'm happy to engage in any questions and discussions or your thoughts on this topic. Thank you very much. And I'm sorry for the interruptions that I was told happened. Thank you.
Not a problem, Yusuf. Thank you so much for sharing with us today. It's very interesting, and I think it's a very topical potential solution to manage plastic pollution. But obviously, it comes with a lot of questions that haven't quite been answered, and not everyone will necessarily, not by you, but just in general, that haven't that I think a lot of people feel there hasn't necessarily been enough research done into it as of yet, which is why we're very happy that you could join us today to shed some light on it. There is a question that's come through so far that says, thank you very much, Yusuf, very interesting and very exciting. Pyrolysis looks like a silver bullet to end Africa's plastic pollution woes. So 1, why is it not implemented more widely? And 2, are there drawbacks or negative impacts for the technology?
All right. Thank you very much. That's a wonderful question, actually. Yeah, pyrolysis has been considered by a number of industries. But again, one thing with technology is you always tend to move towards what has been fully established. The fact that the petrochemical industry has had a stand, it has stood the test of time, actually makes other conversion technologies a bit challenging. Let's not forget, pyrolysis could also be integrated in certain petrochemical industries. And it's not magic, it's being done actually, where you have a lot of heavy materials, the butamens, or your tire pyrolysis. For instance, I'm not sure if you are aware of Redisa, there were projects actually that were done, and pyrolysis of tire waste is among those that is being considered. But remember, the products also have to undergo some transformation, and that is partly part of the challenges. People will say, well, but we have an existing refinery. I mean, the cost of starting a refinery is not something that you will just say you can just do it off if you have one that is existing. So I believe it's just a matter of time. It will gain grounds, but in the meantime, actually, it's part of those that is actually being challenged by the fossil industry, just like the renewable, which seems to be better.
Okay, interesting. So there's another question here that says, thank you very much, very interesting presentation. What are your thoughts on biochemical processes to degrade plastic, like using bacterial strains to degrade PET into valuable compounds like e.g. TPA and even vanillin?
All right, that has a lot of prospects. However, we need to also know that actually we have to get the right strain of bacteria, and what further interactions will bacteria have with the environment. That is something that needs to be looked into as well, actually, because it doesn't end there. You know, is it kind of converted in the bacteria fully, or it gets transported or transmitted to some other material? That is something that actually needs to be considered as well. Was I audible enough?
Yes, I hear there was a little bit of an issue on your side there with the audio, but it's fine. We could hear the answer. Are you able to comment at all on how common thermochemical solutions are in South Africa at the moment between pyrolysis and gasification? Is it quite common, or is it still quite a way to go before it's used? Obviously, we have fuel limitations, so is it quite common given our current situation?
Well, definitely coal. South Africa is coal-based as far as energy is concerned, and that is where gasification holds. In terms of plastics, no, but in terms of other materials like coal, I think it's one of the most developed in the world, actually, because this is where you have the CTL, coal to liquid processes. Sasol technology is basically based on that.
Okay, very interesting. We have another question here that says, thank you for the interesting presentation. Are there losses associated with the thermochemical approaches, as is with the conventional recycling processes?
Very true. But one thing I can tell you is with the mechanical, in terms of the losses that lead to emissions, thermochemical processes are about 7 times more than that of the mechanical. So definitely thermochemical.
Well, we still have you, Yusuf. Can you comment on what kinds of plastic and what kinds of materials are an option for thermochemical approaches. So the photos that you showed, but would
Yes.
the tires be an option, or would there be specific kinds of plastic? Could you have mixed plastics used in a similar batch?
Yeah, so that's one of the things I mentioned about pyrolysis. Provided there is some carbon and hydrogen, perfect. And all these plastics are made up of carbon and hydrogen. The problem has to do with the additives, like the PVC, you have chlorine there. So the fewer the additives, the better. All of them can be used in thermochemical conversion processes.
Okay. And thermoset plastics, would those be an option, or would that not break down in the system in the same way?
Well, they will break down, but let's remember thermochemical processes, we are converting them completely. So even if they break down, it's not a problem. We are changing them completely. So they are all options.
All right. And then you mentioned the byproducts with the tar and char that will come from gasification, I believe.
No, from pyrolysis.
From pyrolysis, sorry.
Yes.
So would there be applications for that, or would that purely go to landfill, specifically the char, I suppose? Okay.
Your char is as good as an activated carbon. It's a porous material. You can use it actually for purification. They are using purification tanks, actually, activated carbon. So when you want to, for filtration purposes, it's an excellent thing. And your tars is the same product you use on your coal tar, and they can be used actually on treating your road surfaces.
Okay, very interesting. And what you shared about the biochar is also quite interesting, that it acts as a fertilizer, as it were.
Yes, yes.
Okay.
Because it has good porosity, and basically it's able to retain some nutrients and let some go through. That's what makes it actually a good option.
Okay. I don't see any further questions at the moment, but perhaps just as a closing question, can you comment on your opinion on whether or not the thermochemical solutions are a circular approach? Because obviously, if you have sort of PET bottles that you're recycling and turning back into PET bottles, ideally that is a more circular option. Obviously, we know that's not the reality for many different kinds of plastics, and definitely in South Africa, it's not what happens to the majority of our plastic. But can you comment on the circular nature of thermochemical options?
Well, in the short term, they are, because we don't have better solutions. In the long term, they may not be. But for now, they're a better option for sure. Because you're talking about 60% that we do not know how to manage. That is it.
Okay. Thank you so much, Yusuf. It's been very interesting, and I think it's been very enlightening in terms of the different options and their byproducts and the potential that they have. So again, if anyone does have any further questions, you're welcome to send those through. I know that our Norwegian attendees may have a bit more experience with using waste to generate electricity, as I believe, waste to energy, as I believe that's how a lot of their electricity and heating is generated. All right. Well, if anyone does have any further questions, I think between our time running slightly over and the interruptions in the connection, please rather email those through, and then we'll close off the session for today once Yusuf returns. But thank you so much, everyone, for joining us today. There will be another webinar at the same time next week. We will email through the link to all of those who have registered for the future links in the series, and then the SST events page will also have the links to register for future sessions. Thank you, everyone. Enjoy the rest of your Wednesday, and we look forward to seeing you next week. Bye-bye.